Okay, welcome everybody. We're starting in on a new topic, but before we do that, we're going to finish up the only last thing I really want to talk about when we talk about lines, and that is how to solve the system of two linear equations. Again, this is probably something you've seen before in Algebra 1 or Geometry. I hope so, but I want to make sure we clear it all up and we're really good at it so when we get to other kinds of equations, we feel really solid about these at least. Okay, so we're going to do three things. We're going to identify what a graphical solution to two equations looks like. Okay, we're going to solve for the solution of two linear equations using elimination and using substitution. Okay, so for many of you, hopefully this looks like something simple, and for those of you who it doesn't, this should be a good review, or perhaps something new, and hopefully we can build some confidence in these methods because I think that may be lacking. So first things first. We have two equations. The equations are x squared and this thing over here, which is a fourth degree polynomial. Okay, and what I've done here is I want to figure out, well, if I'm asking what does it mean to have a solution between two equations, okay, this equation and this equation. What it means is that if I graph the two, okay, and I see the solutions here, I have a solution right here at an intersection and another one right here at the other intersection. So really a solution to two equations is where do they intersect. Another way to think about that is what points do they have in common. Okay, so this graph, which is the one like this, okay, the one facing downward you could say, okay, and that doesn't look very good, and this one, the parabola x squared, the places where they have common points are their intersections and therefore their solutions. Okay, so this is going to be true with lines as well. Okay, if I manage to graph two lines, which you know how to do at this point, I have a line like this and a line like this, as long as there's no gap in it, then the solution to these two, to the system of these two equations is graphically speaking where they intersect. It's the only point they have in common. And let's just make the quick point again that these two graphs have 2 points of intersection. Okay, these two graphs have two solutions. Okay, the intersection between these occurs in two places, but between any two lines, they either have one solution, no solutions, or one line, two lines, infinitely many solutions. Okay, this is two lines, different slopes, two lines, same slope, also known as parallel, and this is two lines, same slope and same y-intercept. So these are really two lines that are really the same line. Okay, so this occurs when you have two equations that might look different initially, but when you actually graph them, you realize they're really the exact same equation, just in a different form. Okay, so sometimes you'll see that, in which case if you ask about where are these two objects the same, they're the same everywhere. Okay, so a way to think about this is what in a solution to two equations, a system of two equations is where are they the same? Okay, so let's move on. We're going to be able to solve for the solution of two linear equations using elimination. Here's the way that I like to think about it. I think of it in 4 steps. The book thinks of it in 3 steps. The first thing we always do is we multiply, and again, now we're looking at only lines, linear. Okay, so we're going to forget about parabolas and cortex and all that stuff for a few minutes and just talk about lines. So we're going to multiply one or both of the equations by a constant to obtain coefficients of x or y that differ by only a sign. So you should be writing this down. This is something that needs to go in your notes. Step 2 is to add the revised equations together. Okay, you might not have done anything to one of the equations, okay, but you're going to have two equations, one of which you may have altered, okay, or two, you might have altered both of them, and you're going to add the new equations together. If you've done it properly, then one of the variables when you add together will drop out, and you'll be left with only one variable. The third step is to take that new equation and solve for that remaining variable. Okay, And then the fourth step is to plug that result back into one of the original equations. Doesn't really matter which one you choose, to find the value of the other variable. All right. All right, so here's my equations I'm going to look at. 3x minus 7y equals 10 and 6x minus 8y equals 8. And before I start, I want to get a quick graphical idea of what these two look like. So I'm going to go ahead and sketch a graph just real quickly to get a sense of what this might look like, where I think my solution might be. Okay, first of all, for this first equation, I'm going to graph my first equation in red. Okay, the first equation, if I let y equal 0, x will be 10 over 3, which is a little bigger than 3. So 1, 2, 3, right over there. Okay. If I let x equal 0, y will be 10 over 7, which is a little bigger than, sorry, negative 10 over 7, which will be a little bigger than 1. So something like that. Okay. My second line, which I'll do in blue, if I let x equal 0, then y equals negative 1, right there. And if I let y equal 0, then x is going to be, again, a little bigger than 1. Somewhere in here. So I see that my lines are going to intersect somewhere over here, okay? Just to get a visual of where we're going to be looking here. Okay, so let's go ahead and try to solve this problem using elimination. So the first thing we do is we're going to look for a variable to eliminate. Oh, my daughter's awake, but I think she'll probably go right back to sleep. So, okay, so I'm going to look for a variable to eliminate. I notice here that 3 is half of 6, or conversely, 6 is 2 times 3. So those are pretty similar. These, oh man, to get these to be the same, I'd have to multiply by something big, something, I'd have to multiply this by 8 and this by 7. So I'm going to multiply the top equation by negative 2. That's what that looks like. Multiply the top equation by negative 2, and I'm going to leave the bottom equation as it is. Okay, so I multiply both sides. If I multiply an equation, both sides by the same number, okay, I'm going to get equality still. So this is the same equation in a different form as this equation. If I distribute the negative 2 on the left and multiply on the right, I get negative 6x plus 14y equals negative 20. And the bottom equation is still the same. Okay, these are the same two equations except that this one is in a different form as this, but they mean the same thing. They're the same line. Okay, if I solve those two, I'm going to get the same exact thing no matter how I do it. Okay. So now what I'm going to do is I'm going to add these two together. So I've done the first step where I've identified one, multiplied one equation by a number, so that now, look what happens. If I add the x's together, I get 0 x's, and if I add the others together, I get 6y, and on the right, I get negative 12. So when I'm adding these together, I add the x's together, I add the y's together. I'm really just doing, this is like plain old addition. And I add the equals together. Okay? This only really works this way if you line up the variables in the correct order. I need to write x, then y, then equals, then a number. Okay? I have to be consistent. I can't make this, it's not going to work quite right if you put the y here and the x here, okay, and they're mismatched. Okay, so I have 0 x's, that's just 0, 6 y's, and a negative 12. Okay, so I just kind of simplified that. Now I have something easy to solve. 6y equals negative 12. We know that's negative 2. Good. I've found that the y variable, okay, is going to be negative 2. That looks about right. Okay. Now what I do is I've gotten that much. I'm almost done, but this is a point. So I need to plug that back into one of my equations. The first equation looks easier to me, so I'm going to use that. Okay, I plug it in, and I get 3x minus 7 times negative 2 equals 10. That simplifies to 3x plus 14 equals 10. So x is therefore negative 4 over 3. So again, that looks about right. Negative 4/3 is right about there. So I have a solution. My solution is a point. Negative, oh, I'm sorry, this should have been negative 4/3 here, because that's the x, and that's the negative 2. Okay, negative 4/3 is x, and negative 2 is y. Okay, so our solution is a point, and this point is the point that's common to both of these equations. If I want to check that, Okay, I need to plug this point into the first equation. Make sure that it is true that if I plug in a negative 2 in for x and a negative 4/3 in for y, that I get the number 10. And I need to plug it back into the second equation and make sure that if I plug a negative 2 in for x and a negative 4/3 in for 8 for y, I get positive 8. Okay? If that works, then this is going to check out. It does work, but we're gonna go on faith at this point. Okay, so if I ask you to check it, what that means is to plug this point into both this line and verify that it is a point on both lines. Good. Let's look at substitution. Now I did elimination first for a particular reason. Okay, I'll explain it in a moment. For my steps, the first one is to solve one of the equations explicitly for x or for y. Step 2. Substitute the new expression into the other equation. Okay. Step 3 is to solve for the remaining variable. And step 4 is to plug your solution into one of the original equations to find the other variable. Notice that the last two here are virtually identical to the steps that we did for elimination. It's only the first two steps that differ. Okay, here are my two equations. Now, notice I could absolutely use elimination here. I would personally multiply the bottom equation by negative 2 and eliminate x. That's an option. Okay, it's going to depend on what I'm asking you to do and which one you think is easier. But we're going to use substitution to solve this. So the first thing to do is to choose one of the equations, okay, and solve that equation either for x or for y. Now, to me, the obvious choice is to solve the bottom equation for x. So I'm going to have x equals, and here's how I do it, right? X equals 3 minus 3y. Okay, good. So I've got x equals 3 minus 3y. Now I'm going to take this x because this is x. Okay, and if we're assuming that these two equations somehow combine and therefore they intersect, then this x, I'm looking for the x that is common between both equations, so I should be able to plug this in to my first equation. I should be able to plug it into this equation. Okay, here's my first equation. Okay, so I should be able to plug this in for x because this is x. That's what equality means. They are identical objects. So that's what I'm doing. I'm going to plug in 3 minus 3y in where x is in the first equation. There it is. 3 minus 3y in for x. That used to be x. Now it's 3 minus 3y because x is 3 minus 3y. All right, good. Now I have an equation. Notice this equation only has y's in it. This is algebra 1. Okay? I simplify by distributing, combine like terms. Negative 6y plus 5y is negative y. Move the 6 to the other side, you get y. Negative y equals negative 11, which means that y equals positive 11. Okay? Now, I got my y variable, my y value. Something comma y. So now I choose to put this back into one of my equations here, either into this equation or into this equation. I have to put it back into the original equation. It won't help me to put it back into one of these equations in here because I'm looking for x and neither of these have an x in them. I have to put it back in somewhere where I used to see an x. I'm going to choose to put it back into this equation. You could have chosen this, you could have chosen this. Okay? So I'm going to choose to put it into this equation here. So I substitute, again, y must go into one of those equations. So y is 11, so I put y equals 11 in here. Okay? There's y. Y is 11, so I put it in there, and I get x plus 33 equals 3. And so I end up getting x equals negative 30. And again, we can graph these, and we'll see that the point of intersection between this line and this line is negative 30, comma 11. Okay? So the graphical interpretation is really important, okay? Because if you don't understand physically what's happening, it's really hard to justify why we do all these crazy steps. Okay? A couple things to notice here. There's a couple things I want you to think about as we're doing these problems here. They're both very different ways to do things. In what cases would you rather use elimination, and what cases would you rather use substitution? Now, I'll tell you a little story that when I remember taking Algebra 2 and pre-calculus and calculus and all those classes, and I remember thinking, why would anybody ever use elimination? Substitution to me seemed a lot easier. Okay? Now, Looking back at it, I'm not really sure why I thought that, but I can understand how many of you might feel that way as well, where substitution seems so much more simple. Okay, but let's look at them together. One thing about the elimination method is that it's very mechanical. Okay, I start with my equations set up, I multiply one of the equations, and then I add them together, and lo and behold, I have something as simple as 6y equals negative 12. Okay, that's really only algebra that has to be done here. 6y equals negative 12, and then I get y equals negative 2. Once I get to this point, once I've solved for one variable, both elimination and substitution require the same amount of algebra after that. So we look at this, and while, yeah, it might seem a little tricky setting things up, at the end of the day, you're solving 6y equals negative 12. That's not so bad. Let's look at substitution. Here, first of all, I have to do some algebra to solve for a variable. Okay? Then I have to take that information and plug it back into the first equation. Then it's going to require some algebra. Distribution, combining like terms, moving things around, multiplying by a negative 1. Boom. And at this point, remember that this is, once I get one variable, the amount of work is exactly identical no matter which method you're using. The last step is always the same. So one thing about substitution is that there is more algebra to be done, and therefore there is more opportunity for little mistakes to be made. So that's just one thing to keep in mind when you're doing this, is that it requires actually more algebra than the elimination method, depending on how it's set up. So that's point number one. The second point is that when you're deciding which one to use, an important factor in deciding is thinking, how much work is it going to require to solve for either x here, or to solve for either y here or here. Now the amount of work that's going to be required is going to be quite a bit with these, and you're going to end up with some pretty weird fractions. Okay, that's a problem here. That's why elimination is a much nicer method to use in this case. We avoid fractions all the way until the very end. Now, I love fractions. I'm sure you love fractions. But if you can get around having to use them, why not? Okay. So here, if I were to use substitution, I would have to be forced to deal with lots and lots of fractions. Okay. This method is usually pretty good when it's easy to solve for x or easy to solve for y. Notice here, x is not multiplied by anything. So I knew right away that it would be pretty easy to solve for x. Okay, so that's a thought as well. Solving for x in this case would probably be rather difficult. Okay, not rather difficult, but you'd end up with fractions like 5 over 2. I could solve for y, but again, I'd end up with fractions. Okay, so using elimination eliminates having to use many fractions at the very beginning. Okay, eliminates introducing fractions into the equation, whereas substitution is a really good method if it's super easy and super clean to solve for one of the variables. Okay, so you want to be thinking about, well, which method is going to make the most sense for my problem, for my context. Because at the end of the day, if somebody gives you a problem, nobody cares how you got from the two equations to the solution, but you want to make sure you do the most efficient, okay, and hopefully the easiest method available. Okay, so that's it for now. We'll see you in class.